Matrix decomposition is a fundamental concept in linear algebra, and today we'll explore two key methods, spectral decomposition and singular value decomposition. These techniques help us break down matrices into simpler, more manageable components. Spectral decomposition. What is spectral? The set of eigenvalues of a matrix is referred to as its spectrum. Spectral decomposition means breaking the matrix apart using its spectrum. Spectral decomposition is a method of expressing a square matrix in terms of its eigenvalues and eigenvectors. For a real symmetric, or complex Hermitian, matrix A, there exists an orthogonal, or unitary, matrix Q such that A can be written as a product of Q times lambda matrix times Q transpose, where Q equals matrix whose columns are orthonormal eigenvectors of A, lambda equals diagonal matrix with eigenvalues of A on the diagonal. This is called the spectral theorem. Let's dive into an example of spectral decomposition. Here, matrix A is symmetric, as A equals a transpose. The eigenvalues of A are the solutions of the characteristic polynomial, which is obtained by putting the determinant of the matrix, A minus lambda times I equal to 0. Solving, we get eigenvalues 3 and 1. The eigenvector corresponding to 3 is a non-zero solution of the matrix equation, A minus 3 times I equal to 0. Solving we the eigenvector. This vector is not normalized, so to normalize, we divide this vector by its length. So normalized V1 is given by. Continuing with our example, we solve for the eigenvectors associated with lambda equals to 1 and find the normalized eigenvector version 2. Thus, the matrix Q is formed by taking V1 and V2 as column vectors. So by definition, the following is the spectral decomposition of A. Singular value decomposition, SVD, is another powerful matrix factorization technique. It breaks down a matrix into three components, two orthogonal matrices and a diagonal matrix, providing insights into the matrix's structure. Here, U is an M by M orthogonal matrix, V is an N by N orthogonal matrix, and sigma is an M by N diagonal matrix. The following are the steps to compute the singular value decomposition of a matrix A. First, compute the transpose of A times A, which is an N by N symmetric matrix. Find its eigenvalues and eigenvectors. The normalized eigenvectors of transpose of A times A form the columns of V. The square roots of eigenvalues are called singular values and denoted by sigma I. Second, order the singular values, sort eigenvalues in descending order. Singular value sigma I is equal to the square root of lambda I. Put them in descending order in the diagonal matrix of sigma. Third, compute matrix A times A transpose, which is an M by M symmetric matrix. Find its eigenvalues and eigenvectors. The normalized eigenvectors of matrix are multiplied by a transpose form the columns of U. Let's explore an example of singular value decomposition. Here, A is a 3 by 2 matrix. We start with computing the transpose of A times A and then find the eigenvalues of it. Here it comes to be 9 and 4. Now, the singular values are the square root of these eigenvalues. The sigma matrix of order 3 by 2 is formed by putting these singular values on the diagonal in descending order. To obtain V, we find the eigenvector corresponding to the eigenvalues. We then normalize these eigenvectors and make columns of V. Now we compute A times transpose of A and repeat the same process. The final result of the SVD process is a matrix expressed in terms of U, sigma, and V. This decomposition is not only mathematically elegant but also practical, with applications in data compression, noise reduction, and uncovering hidden patterns. In our next lecture, we'll delve deeper into these applications.